All right, so we're going to do a little recap of what a, k, d, and c can do to our functions. Here, we are using parent functions in the form y equals x to the n, where n is a number equal to or greater than 1 that is whole. So all the counting numbers, 1, 2, 3, 4, and so on. That means that in this equation that I'm showing here, the n is not a transformation. The n represents the x to the n power function. Okay, so it represents the parent function. The transformations are the a, k, d, and c. All right, so we have a, which is a vertical change. And that means it's a change to the y's. And there's three things that a could possibly do to our function. It could be a vertical stretch, a vertical compression, or a vertical reflection. I can have also like a stretch and reflection, or a stretch and compression at the same time. Or sorry, not stretch and compression, compression and reflection at the same time. So if a is greater than 1 or less than -1, this will cause a stretch to happen. If a is between -1 and 0, or 0 and 1, this is going to cause a vertical compression to happen. And if a is less than 0, or in other words, a is negative, this will cause the reflection part to happen. Okay, so essentially I'm saying for this part here, if a falls in this range or this range, then we know that it's a stretch and reflection or a compression and reflection. So I only look at whether it's negative or positive to decide on the reflection part of this. So that's our A. K is very similar. It can cause compressions, reflections, and stretches, but it's in the horizontal direction, so the x direction. And it's kind of like k and a are kind of opposite of one another. So if k were to be greater than 1 or less than -1, this one actually causes a compression to happen. Whereas when a is greater than 1 or less than 1, it causes a vertical stretch to happen. Okay, and then similarly, if k is between 0 and 1, or and -1 or 0, then we'll have a horizontal stretch that happens. Okay, and if k is negative, so in other words, less than 0, this is going to cause a horizontal reflection to happen. So again, I can have combinations of these things, right? I can have a horizontal compression and reflection at the same time. I can have a horizontal stretch and reflection. I cannot have a compression and stretch at the same time, because those are two opposite things. Okay, for the d value, because of this negative here, we always need to remember when we're stating the d value, we switch the sign. If you guys remember that from last year. So switch the sign you see in the equation. And once you've switched that sign, if d is positive, this is going to be a shift to the right. Or in other words, if it's greater than 0, you shift to the right. If d is negative, or in other words, less than 0, we shift to the left. Okay, after we've switched the sign that we see in the equation. Okay, and then our last one is C. C is very straightforward. If C is positive, we shift up. that number of units. If C is negative, we shift down that number of units. So C is a vertical change, D is a horizontal change. Okay, so that's kind of like our recap in grade 11. If you remember, this was kind of like a big part of the course in grade 11. We did like a whole unit on this, and then we returned to it. We did transformations of exponential functions, and then we returned to it again when we did trig functions. So hopefully this is like somewhat familiar to you. Might take a little bit just to kind of get yourself reminded of it, but we definitely did do it quite a bit in grade 11. So. Okay, so all we're going to be focusing in on for this unit is transformations of these base power functions. So y equals x to the n. And the nice thing is I don't have to memorize like any key points for these or anything like that. Some really good x's that you can choose for literally any power function. So y equals x squared, y equals x cubed, and so on. You can just choose the same ones for all of them. And I think -2 to +2 just gives us like a good range. It will give us some points on the left, some points on the right, and we'll get a decent idea of what that graph looks like. Then I find the y's by plugging into whatever the parent function equation is. So I will sub in the x's into y equals x to the n, whatever that n is. So you calculate these. Or we'll say use the parent function and calculate the y's. Okay, obviously those y's will change if the exponent changes. If the exponent's 2 versus 3 versus 4, the y's will be different. You can keep the same x's. So that's all I need to know, -2 to +2. And then I'm good to go for any power function. Not too hard to remember, right? It's not too bad. Okay, couple reminders about the k-value. First, the k-value needs to be in this format here, which is common factored out from the x and d. If I don't have that, I won't see the proper d value shift. So make sure k is common factored out. Okay, so I need to be able to see k bracket x minus or plus d or whatever that is. Okay, if you don't see that kind of format in your transformation equation, you need to common factor it yourself. The other thing is that when I go to calculate transformations, I always use reciprocal of k. Okay, not when I state k. If I'm just listing what is a k dc, I use the regular, what I see in the equation. But when you calculate, you use the reciprocal of k. Trent?
How do you determine if it's a
You will see it included in brackets with like the exponent on it if it's a k. If it's an a, it won't be included inside that exponent. Does that make sense? Okay. Athena? Yeah? So when I say reciprocal, for some reason, from our grade 9, like lines that we did, we got like negative reciprocal ingrained in our minds. Negative reciprocal you will not see again until you do like vectors in calculus, if you do calculus. We're just using reciprocal. So what's the difference between negative reciprocal and reciprocal? What am I talking about here? Oliver?
It's like if there was like 1/2, then the negative reciprocal would be like -2. So you flip it and you add a negative to it.
Okay.
The reciprocal would just be
Okay, perfect. So I don't switch the sign for just a regular reciprocal. For negative reciprocal, we flip it and also switch the sign. For reciprocal, we just flip it, the sign remains the same, okay? So no negative reciprocal. Just block that from your mind until you go into calculus, if you go into calculus. If you're not taking calculus, just erase it from your mind now, okay? All right, so I want to do just like a quick recap. How do we state transformations in words? How do we list AKDC? And this also asks, make sure they're listed in the proper order. What did we talk about back in grade 11 about proper order of transformations? Which ones have to happen first? Which ones have to happen at the end? Lexi? Yes. Yeah. I always just say work your way left to right, right? Because we have to do all stretches, compressions, and flips first, and then we do all translations or shifts last. Okay, so I'm going to just work my way left to right here. We're going to start with the A value. So here A is -2. If you need to for now, as you're reminding yourself of what we learned in grade 11, you can look at these guidelines here, and then you can make a decision. So where does -2 fall here? And do we have a combination of things here? So find where -2 would fall and make a decision. Somebody tell me what an A value of -2 is going to do to our graph here. Esther? Okay, perfect. So it is I just totally don't even know what I'm writing here. It is a vertical reflection. That's the negative part. Okay, and it is a vertical stretch by a factor of 2. Why do I not say by a factor of -2? Alicia? Yep, so the reflection part is the negative part. The stretch part is the 2 part of this. Perfect. Okay, K value. What should I state the K value as? Is it 1/3 or is it the reciprocal that I state it as when I list the K value? Lucas?
State it as 1/3, and then when you do the transformation, you use 3.
Perfect. And when I list it in words, I will use the reciprocal as well. Very good. So what does the K value of 1/3 do to our graph? Okay, if you need to, look above, see where it falls in all of these little statements here, and then make a sentence based on that. Tina, you want to do this one?
Increase a horizontal contraction by factor 3.
Close.
Is still on 3.
The 3 was right.
Oh.
Horizontal stretch by a factor of 3. So I like to just think of this, like once I do the reciprocal, if I'm saying stretch, it's going to be a value, like the reciprocal will be a value that's greater than 1. If I say it's a horizontal compression, when I do the reciprocal, it'll be like a value in between 0 and 1. And obviously that can be -2. Okay, so horizontal stretch. If we look back up here, we can see 1/3 falls in between 0 and 1, so this should be a stretch. Okay, what do I state the D value as here? D equals, Oscar? +1, switch the sign. That's the only one we actually like kind of switch from what we see in the equation. So this must shift right 1 unit. And the last one, what is C? What does it do? Vicky? Victoria, sorry. I don't know if people call you Vicky.
5.
Yep,
And then shifts up 5 units.
perfect. Shift up 5 units. Any questions on this? So maybe we'll just make ourselves a little note here. When we use this value in the actual sentence, we're going to use the reciprocal of k. Billy?
Does it change anything that
That will change what parent function we use, the cubed part, versus like squared or to the exponent 4. So it just gives us an indication of what we, actually this one asks us to identify the parent function, so we should do that too. Sentence. Okay, so what is the parent function here, now that Billy has posed this question here? What does this tell me about the parent function? Athena? Perfect. So the cubed tells me that our parent function is y equals x cubed, or f at x equals x cubed, whatever you want to call it. It's not a transformation, right? It just tells me which of my power functions do I want to start with and apply these transformations to. So that's what we're going to use on the next page here when we go to graph and calculate the points. Okay, so find some key points for that parent function that we just identified, and then we're going to remind ourselves how we do transformations, how we calculate them. So here's our parent function. Some x's that we choose that are easy to use for any power function, -2 to +2. And then I will plug them in to find my y's by just cubing all of those x's. So if the exponent were 2, or 4, or 5, I'm plugging in the same x's, but I'm getting out different y values here. So you're going to take each of these x's and cube them, get your y's. Okay, so -2 cubed, -8, -1 cubed, -1, 0 cubed, 0, 1 cubed, 1, 2 cubed, 8. Okay, let's remind ourselves how we set these equations up for the tops of our table of values based on, again, we're using this equation here, AKDC. Oscar. I know that can't be more exciting than this. Obviously not. Okay, so we are going to use reciprocal of k times x plus d. This is the switched version of d, right, after we've switched the sign. And then we will do the y's are the vertical changes, so a times y plus c when we create these equations. These are really nice because what it does for us is it does all the stretches, compressions, and reflections for us first because of bed mass. Those are just multiples, right? We do multiples first. And then when we add c and d, it does the stretches for us, or sorry, the shifts for us after. And then it just takes care of all of that order of transformations all together, and we get the new points so that we don't have to do like step by step every transformation and do new calculations every time. So given these now, these two equations, can somebody set up the x or y equation for me? Just one of them. Oscar? Sure. Perfect. So reciprocal of k, opposite sign of d that we see in the equation, and then can somebody do the y side for us? Athena? -2y plus 5. Perfect. So I'm going to give you guys a second. Everyone should have a calculator that they can use for this if they need it, or just try it in your head. We are going to take now each of these x's from our parent function, and we're going to put them into the x here and calculate the new x's. Once we've done that, we'll take the y's from our parent function, and we will sub them in to the y here, and we'll find the new y's. Okay, so take a second to calculate here. Correct me if I'm wrong on these, but I just did these in my head. I got this. Am I good? I see some nods, so I like that. That's good. Perfect. Okay, so we took each of the x's, multiplied them by 3, added 1, took each of the y's, multiplied by -2, add 5. We are going to graph both the parent function and transformed function. So I'm going to do the parent function first here. -2, -8. I'll do these in 2 different colors. -1, -1, that's like right here. 0, 0, 1, 1, and 2, 8. Should look like that kind of general cubic that we talked about on the first day. It just is like a slight S shape. So nice smooth curves here, no like zigzags or anything like that. Should be something like this. I'm going to label this as f at x equals x cubed. And then I'm going to start graphing the transformed function. As soon as I can get this to be quiet. There we go. -5, 21. -2, 7. It's here. 1, 5. 4, 3. And 7, -11, which is here. Yes. This should always follow the same general shape of the parent function. This one was vertically reflected. We had some stretches, compressions, stuff like that, shifts. Make sure that it actually was shifted right and up 5. Okay, that was what it was supposed to be, based on what we listed in our transformations, and then nice smooth curves here. And I'm going to label this as the equation from the first part of the question here. Okay, any questions on this one? Can I clarify anything here? Is this sort of coming back into your memories from last year, a little bit at least? That's good. Very cool. Yep, go for it. Okay, so for this one, determine parent function, we're going to list the transformations. Decide on some good key points. We're not going to graph this fully. We're just going to do a general sketch. So we're going to kind of imagine, based on our list of transformations, what's going to happen here. And we'll identify some information. This we will save for our review day. And then we're going to talk about this briefly. Okay, so almost to the end here. Okay, what is the parent function given this equation? Maybe someone who hasn't participated yet today. I feel like I'm getting the same 4 people raising their hands a lot here. What is the parent function? Jess. X to the 4. So this exponent tells me that we have y equals x to the 4, or we can call it f at x equals x to the 4. So this is not a transformation, right? When I list the transformations, I'm not going to include that as like a possible transformation. Okay, there's one problem with how this equation has been presented to us. What is the problem here? Esther. Okay, So k must be common factored from x and d. So I will have to take that 3 out, and we should have actually x plus 2 in the brackets here. If I don't do that, it looks like d is negative 6, but d is actually negative 2, right? Okay, so just quickly here, I want to know what is A, what is K, what is D, what is C. So who can tell us what each of those is here? I'll give you guys a second to think about it as I write this down. Okay, so A, K, D, C. Billy, go for it. So just give me the numbers for right now. Yep. Yep. Okay. Awesome. And he was right. A is a vertical reflection. Is there a stretch or compression here at all? Athena, why are you shaking your head no?
Because A has to be either more than 1 or less than 1 to be a stretch, and then it has to be in between -1 and 0 or in between 0 and 1 to be a compression.
Okay, so it doesn't fall within any of those. All it falls in is that it's negative. So it's just a vertical reflection. Think about it this way. If I multiply things by 1, do they change? The numbers don't change, right? They don't grow, they don't shrink. If I multiply it by -1, yes, the positives become negative and the negatives become positive, but they still don't change their number values, right? They don't get bigger, they don't get smaller. So just vertical reflection. Lucas, did you have a question?
I was going to say.
Okay, perfect. All right, k value of 3, what does this do to our graph? And how do we say it in a sentence? Lucas?
Horizontal stretch.
Not stretch. It's opposite of what you think. Horizontal compression, and then what do I say, Oliver? By a factor of? Yes. Yep, you're right. By a factor of the reciprocal. We use the reciprocal, so 1/3. So if I'm saying compression, I'm always going to be saying by a factor of something in between like a 0 and 1 or a -1 and 0 value. If I say stretch, I'm always going to be saying like horizontal stretch or vertical stretch by a factor of something that is greater than 1 or less than -1. Okay, last two. D value of -2. Lexi? Shift left 2 units. And the last one. Sophia? Perfect. Shift down 1 unit. I do not need to say like shift down -1 units because the down is the negative part or the left is the negative part. So I don't say like shift left -2 units because the left is the direction of shift. Lucas?
Just a question, I'm sorry. So is the compression, is that referring to the 3 then or to the 1/3?
So if you look here, I am telling you that, so we have, for instance, a 3, right? So 3 falls, where does it fall in these expressions here?
Falls under compression.
Okay, so it's greater than 1, right?
Oh.
So it should be compression.
I thought it was between 0 and 1 because it's 30.
So we're looking at the actual value that we see in the equation for this, and then when we state the transformation, we'll use reciprocal. Yeah, that one's like a little bit confusing. But I like to just remember like it's kind of opposite of what I would expect for A. Okay, any other questions on this so far? Okay, can I scroll? You good, Lucas?
Yep.
Okay. What are some good points to transform this f at x equals x to the 4 parent function? So what x's do I choose here? Lexi? -2 to 2. And I will calculate the y's by subbing in and putting them to the exponent 4. When you put these to the exponent 4, it is very important in your calculator that you do one of these two things. Which way should I enter this into my calculator? Carol? The top one. Why? Athena?
Because if we don't put the negative in brackets, then it's just going to assume that the negative's not the part that's being with the negative 4, so it's going to keep it.
Yeah. So if I don't put it in brackets, Athena said, my calculator is going to assume that I'm only putting 2 to the exponent 4, and it actually just leaves the exponent in front. Some of your calculators might automatically put brackets around it sometimes, like if you hit the exponent button, but a lot of them will, if you don't put that bracket there, it will just put the 2 to the 4 and then leave the negative in front. So we want to make sure we're doing this, especially for all the negatives, put those brackets around. Okay, so if I put something to an even exponent, it's actually going to multiply by itself an even number of times. So all negatives become positives. So negative 2 to the 4 is 16. Negative 1 to the 4, positive 1. 0 to the 4, 0. 1 to the 4, 1. 2 to the 4, 16. Okay, also use your common sense. We know if we square something or we put it to an exponent 4 or 6 or 8, the negatives will all become positive. Okay? All right, I'm not going to do a full calculation of all the new points and stuff like that. We're just going to sort of use our common sense and our sentences above and create a picture of this. But I do want to just make note of, if I were going to do the calculations, what would my equations look like up here? Just so that we can practice that skill one more time. Just remind ourselves. So I'm going to use this equation here. How do I set up those two transformation equations? Lucas?
Isn't it 1 over 3 times x plus c on the left side,
Mm-hmm.
and then it's ay plus c on the right side?
Mm-hmm. So what is that in terms of this question?
Sorry,
It's okay.
what is it? Okay, so on the left side, it would be 1. So it'd be 1/3
Mm-hmm.
x. That's minus 2.
Yep.
Minus 2. And then on the right side, that's negative 1 y.
Mm-hmm.
Sorry, just negative y.
Yep.
In that case. And then minus 1.
Is it minus? Oh yeah, you're right. Minus 1. Perfect. So that's what I would use. I'd plug each of these x's in here, each of these y's in here, and I would calculate. This one's just asking me for a general sketch, so I think that we can sort of just use our common sense here and figure out what that final graph would look like. If you really wanted to, you could calculate the points, but you should also be able to just sort of predict what this might look like as well. So if I try to create a sketch here, I'm starting with that base power function that looks sort of like a quadratic, but it's a little bit more of a squared bottom here. And then if we look at our transformations above, we are going to do a vertical reflection. So I'm just going to sort of show this step by step, but then I'm going to erase the step by steps once I get my final. So I will do a vertical reflection. Then I do a horizontal compression. So imagine you are doing this. So what's going to happen is sort of like this. And then I'm going to do a shift left 2 units and down 1 unit. So take that green graph and shift it left 1, 2, and down 1. And then you'll have your final graph here. Okay, so I'm just going to erase these. We don't really need those steps there, but if it helps you to draw those just to kind of get to your final, that's fine. So this will be at -2, and we shifted down 1, so that will be at -1, where we have that vertex there. Okay, so this would be our parent. This would be our transformed. Okay, so we have our general sketch. state, domain and range, vertex, and axis of symmetry. This one just so happens to have an axis of symmetry because it's like a basic power function and it's symmetrical on both sides. So I want to do domain and range in interval notation just so we can keep that fresh in our minds, that skill. So I'm doing domain and range for this, not the black function. How would I do domain for this in interval notation? It's always lower bound to upper bound. So are there any boundaries on the left? Are there any boundaries on the right? How do I say that? Lexi? Okay. Round bracket? Okay, so lower bound or left boundary. There's no left boundary. It keeps going toward the left forever. Or I guess this is your left. And then upper boundary, there's no right boundary here. There's no high boundary on the x's. So I say it can be anything from negative infinity to positive infinity. Because this keeps widening forever, right? It keeps going toward the left and right forever. There's no gaps in the middle or anything like that. Question? Okay. Okay, range. Think lower, think bottom to top for range. And when I state range, I always want to make sure I do the lower boundary to the upper boundary. So low to high. Lucas, you want to try this one?
Sure. So would it be negative infinity with a round bracket and then -1 with a square bracket?
Jess, do you agree? You agree? He's right. So this goes down forever toward negative infinity, but the highest it can go is up to and including -1. -1 is a point on the graph. So we include that with a square bracket. Infinity, negative infinity, they always need those round brackets. We talked about you can't include them with a square bracket because they're infinite. They go on forever. Okay, vertex. If you locate the shifts will tell you where the vertex is. Oliver? -2, -1. This is now a coordinate, right? We're not doing interval notation anymore. So it's right here. And equation of the axis of symmetry. So we're reminding ourselves kind of some of our grade 10 and grade 11 work with quadratics here. How do I state the axis of symmetry? Athena? X equals whatever number your vertex cuts through on the x. So it's x equals -2. That's the line over which this function is mirrored. You can put it on your sketch if you want. Okay, so always x equals the number that you're cutting through for the x of the vertex. Okay, questions on this one before we briefly do our last example? Okay, so as I said, we're going to save this little activity for our review day. But this one, how do I identify polynomials versus other functions? So in our very first lesson, we talked about like a couple functions that we learned about last year, and then we talked about polynomials. We can have polynomials in expanded form, so we call that standard form. It's all expanded out. We can see each individual term. We can also have polynomials in like kind of like factored form, or even in this like transformation form that we learned about in our lesson here. So they could sort of be like in this format, where we see the power function exponent and then transformations as well. So I want you to put a check on all of the ones in here that you believe to be polynomials. Which of the ones, or circle them, which of the ones here are polynomials? Okay, Caleb, what's one that you circled? Okay, h at x. Kira, what's one that you circled? N at x. Victoria, did you have any more that you circled? F at x. Sorry, there's two Victorias. I'm going to have to say your last names then, or like the letter of your last name. Are there any more? Did anyone circle any others here? What about this one? This has just like an x to a whole number exponent. Is this a polynomial? Is it not a polynomial? How do we know? You guys didn't circle it. Why not? Or maybe you did. What do you think, Lex? Why would it have a different base function? What gives you that indication by looking at the equation? Yeah, so it's a rational function, right? It has like 1 over, and then it gives us the equation. Totally different than a polynomial function. If we have a rational function like this, it's going to produce like a totally different type of graph. This is a square root function. If I were to switch this into an exponent instead of a root, it would be an exponent of a half. For polynomials, we need whole number exponents, so that one cannot be polynomial. What is j at x? What type of function is that? Trig function, or we call these like sinusoidal functions, right? Sine and cosine. So if we see this like sine or cosine or anything like that, not a polynomial function. Okay, so standard form or factored form or even like this transformation form, we might see all of those things in polynomial equations. Okay, any questions? All right.